end last time, so at the end, we had the integral over, what were we calling it when we filled in the first circle and crossed it with the second circle? Was that M?
Yeah, M was both.
M was the filled in thing. And we had the integral of 3x1 squared
X3.
x3
dx1
dx1 wedge dx2 wedge dx3. And because I was running out of time,
dx4.
oops, thank you. Thank you, Don. So because I was running out of time, I just said, well, hand wave, Fubini's theorem, here's the answer. So let me take 3 minutes to show you that. So what we're integrating over here is, first of all, I did talk about how this was the correct orientation, and so at this point it becomes just a, well, okay, so I have to figure out how do I integrate this. And I was suggesting that you should think of this way. You have this 2 form that really lives in the x1, x2 plane. And you have in the circle that's in the x3, x4 plane, you have this one form living there in the x3, x4 plane. And what I'm suggesting is, how would you think about setting this up as an iterated integral?
Iterated integral times another.
Well, so what's happening here? You have what's the region M? It corresponds to having x1 and x2. So I have x1, x2, x3, x4 with x1 squared plus x2 squared less than or equal to 1. That was filling in this circle. I've forgotten what colors we used yesterday, so I'm not going to do them. And then we had the other circle still just on the curve, not filled in. So how would you imagine, if you wanted to integrate over this 3-dimensional manifold, how would you imagine parameterizing it?
Model type. There's a disk in a circle.
Okay. So you want to have how many variables? 3. A disk, 2 variables, and a circle, 1 variable. Okay? So you want to use polar like r theta in the disk,
And phi in the...
and phi in the circle. That's good, Cameron. So everybody agree on that? That you can parameterize this by filling in the disk with usual polar coordinates. And then what's phi? Well, you would have cosine phi, sine phi, but it's a circle of radius 2, so I would have that. Okay? And the orientation that we discussed yesterday, I'm not going to go back through all of that. The orientation is given correctly by taking dr wedge d theta. That's the usual orientation on the x1, x2 plane. And then d phi was giving us the correct orientation on the circle in the x3, x4 plane. Having d phi means you're going counterclockwise around that circle in the x3, x4 plane. So if you pull back, what do we get?
The first one we already theta.
So if I pull this back, I'm going to integrate over what? What's my region, omega, in r theta phi space?
R goes from 0 to 1, theta goes from 0 to pi, d goes from 0 to
Cool. I can't write fast enough, but okay. So you're in 3 space with coordinates r, theta, and phi doing this. And what Cameron is saying is, if we actually pull this back, what will this pull back to? Well, you know how to do this in polar coordinates. This is like 3x squared dx wedge dy. So in polar coordinates, that becomes what?
3r cubed
dr wedge d theta. And then x3 dx4 pulls back to 4, right? Cosine squared phi. And what we're saying is, all right, now I'm just going to write this as a triple integral, where I put dr, d theta, d phi. That's the standard order. I can do the iterated order, integral any order I want. So what have I got? I've got 3r cubed cosine squared theta cosine squared phi. R goes from 0 to 1, theta goes from 0 to 2 pi, phi goes from 0 to 2 pi.
Yeah, one of them before.
Oh, the 4. Okay, so Lama wants me to factor out the 3 as well, but now you've got to do some integrals, all right? Now what you notice at this point is that the limits are all just constants. They don't depend on one another, as you're used to. And this function is just a product. So I can actually think of this as integrating usual polar coordinates to do this. Oops, 3's already there. Yeah, all right, r cubed cosine squared theta dr d theta. And then integral from 0 to 2 pi cosine squared phi d phi. Right? This integral can be pulled out because it's going to do the r theta integral. I'm going to get a number for the answer, and that number will multiply the final phi integral when I do the last iterated integral. So this is what I did yesterday when I said by Fubini's theorem I could sort of separate out this integral because it didn't depend in any way on what was going on in the integral of the disk. Does this help? Whoever it was who asked me about it?
Yeah.
All right, so at this point you can finish it. Now I do confess that the way I was doing it at the end of class, there's a sneakier, easier way to see it, so I'm going to explain that to you. Okay, so you can finish this integral. What did we get? Integral of 12, integral of r cubed from 0 to 1, 1/4, integral of cosine squared from 0 to 2 pi. You guys haven't done this enough because you keep using technology instead of doing it. But integral of cosine squared or sine squared from 0 to 2 pi is always pi. If you do the double angle formula, it comes out, you get a 1/2 theta. So you get a pi from the cosine squared integral here, and you get a pi from the cosine squared integral there, and as promised yesterday, you do get 3 pi squared.
So what you did at the end just justified separating D and C. What we said yesterday.
Yes. But now I'm going to say, now that you understand that if you do the pullback and you get an iterated integral, you can sort of think by Fubini of thinking of it as a product of two integrals. You can actually see that more directly, and you can cheat a little bit here. You would agree then that what I'm ending up doing is just integrating the first two form over the disk, multiplying by the integral over this, what did we call this circle? I forgot.
C.
Was it, this one was C?
Yeah.
Okay. It's 3 dx4. And again, you can think of that because the 3 form we're looking at here is a product of functions independently in the various variables. This doesn't involve x1 or x2 in any way. And similarly, the 1 form here lives only in the x3, x4 plane, and the 2 form here lives only in the x1, x2 plane. So that's what allows you to separate it out. It's analogous to having a function of x times a function of y, dx dy, and the region is a rectangle. Right? It's completely analogous to saying I'm integrating over a rectangle in the xy plane, and I have something that looks like f of x dx, which g of y dy, integrated over the rectangle, then you wouldn't hesitate for a minute to say, oh, it's just the same as integrating f here times integrating g there. That's all we're doing, just in the higher region. Yeah, Patrick.
We had a term that was dx3, which dx2, which dx4, and we just said it was 0 because...
Right, because if you pull back by this parameterization, if you pull back dx3 wedge dx4, there's only one variable there, you're going to get something d phi wedge something d phi, you're going to get 0.
Can this in any way be considered like spherical coordinates, or is it just polar coordinates plus another?
It's like two sets of polar coordinates. And in fact, so what I was going to say is, this you know how to do by switching to polar. And this we did by pulling back and parameterizing. But, did you want to say something?
Yeah, I have another question.
Okay.
Okay, so what if you had dx1, which dx2, which dx3? There's no dx3 in our...
But we still have this parameterization at this point, and you know how to pull back dx3, no
Would
problem.
you write it like in terms... What if you had like a...
No problem.
Okay.
Yeah, no problem. So Justin and Yiming and a few other people, I think, have been concerned about the way I talked about orientation. When I told you that you should orient it by saying, orient the surface by saying dx2 wedge dx4 is positive, what I was really saying is that you orient this circle going counterclockwise and you orient this circle going counterclockwise. And that determines how to handle the orientation question even if you had a dx3 in there.
I knew it was counterclockwise.
Because,
you can see in your picture which one is.
well, because I was at this point here and at this point here, and I was saying that you should go this way and you should go this way to make dx2 which dx4 be positive, or you could make them both be backwards.
And you're going to say, you get two negative signs.
And then you get two negative signs. All right, let me finish this. So if I told you this problem and I said do it without pullback, what would you do? C here now is a circle in the x3, x4 plane of radius 2. How would you do this integral of this one form without parameterizing?
See if I can parameterize in my head.
No. Then I had to integrate cosine squared. That's too hard.
But
It's too hard. How do you integrate, suppose this were just with x's and y's, and we were just in the regular R2, and I told you what's the integral of x dy around this circle?
0.
No. How would you have done this a week ago? Hint, what color is it?
Green's theorem. I'll call you Green's theorem.
Go on, Llama. Green's theorem is now Stoke's theorem, they're all the same.
Guess you would do.
What would you do with the one form? Take d of it, and what would you get? You would get dx3 wedge dx4 integrated over, and I'll call that not d because we already have a d, so I'll call it.
So C is actually like D of whatever.
It's the boundary of this disk, script d, and what are you integrating when you do dx3 wedge dx4 in the x3, x4 plane? What are you computing? Area.
Let's just.
So it's 4 pi. And you say, well, wait, we didn't have a 4 pi in this calculation. Well, the 4 was part of the 12. This 4 was coming from the radius squared of that circle. So it's the same calculation. Okay. Just to alleviate tension in the room, you will not be asked to do 4-dimensional integrals on an exam.
Okay.
That doesn't mean you shouldn't learn it, but this is considered harder stuff. It's not going to be on an exam.
I didn't think it was that bad.
Can you just give us
Come on,
an
I'd rather this than orientation. If you're doing one of these, I don't know
You
where
can't do
orientation.
integrals with it. You can't do surface integrals or integrals on manifolds unorientedly.
Well, if you just set it up so it's all positive, I don't have to worry about it.
I know, I give you the answer, you don't have to worry about it at all.
Absolute value of the answer every time.
Alright, so for those of you who came in late, I have moved problems 7 and 8 from the web work to next week's assignment because the assignment was a little on the long side. So what I'm about to do now, however, is an example of how you would do those problems next week. So here's another question I want to ask you. Alright, consider the unit three-dimensional sphere. Whoops. In 4 space. So this is the set of all unit vectors in R4. There are various fancy ways to think about S3, one of which is to think of it as, by analogy, so this is called S3. Since I'm going to keep saying that, I might as well write it down. It's a 3-dimensional manifold sitting in R4, just like S1 is a 1-dimensional circle sitting in R2, and S2 is a 2-dimensional sphere sitting in R3. So the index is telling you sphere that's a this dimensional manifold. That's
One-dimensional circle.
That's S1. This is S2. And this is S3.
I'm guessing S0 just like 2 points plus minus 1.
But I'm faking you out because this picture is really to be thought of by saying this plane here is a copy of R3 with an extra axis making R4.
Of course.
So you either have to think, when you want to try to picture 4 space, you either have to think about 3-dimensional pictures color-coded, where the 4th variable is your coloring, or you have to think of your 4th variable as time, where you run a movie and see a bunch of 3-dimensional objects varying with time, and that's the 4th variable. Or what I'm going to suggest you will find most constructive is think of it by analogy with R3, where R3 was R2 together with an axis. What coordinate system am I setting you up to think about? R2 together with an axis. Cylindrical. So I'm suggesting you can think naturally of R4 in 4-dimensional cylindrical coordinates.
So you have like small spheres at a point.
Okay. So when you're thinking of R3 together with another variable, which is the 4th variable, how could you naturally work with R3 that's analogous to polar coordinates in R2? You don't have to do it this way, but it's going to be convenient. Spherical. So we're going to use spherical coordinates in R3 together with a 4th variable to understand how to do an integral on this thing. Okay? So I want to think about the unit sphere in 4 space, and I'm going to give you a 3 form. So I'm going to say orient with outward normal. Well, by a complete analogy to what you do with the 2 sphere, what's the unit normal that's pointing outward? It's the position vector at each point. Well, I'm going to do the exact same thing on the 3 sphere in R4. The unit normal is going to be the unit vector x. And you won't be surprised that I can write down a flux 3 form or an area 3 form by a complete analogy with what we've been doing for surfaces. And so I'm going to write this guy down. I'm going to take x1 dx2 wedge dx3 wedge dx4 minus x2 dx1 wedge dx3 wedge dx4 plus x3 dx1 wedge dx2 wedge dx4. I'm running out of blackboard. Plus x4 dx1 wedge dx2 wedge dx3. Do you see that this is analogous to your sigma that you've been using on the 2 sphere? it was x dy wedge dz plus y dz wedge dx. Well, where did this minus come from?
You switch.
Right, I didn't switch here when we did switch for the dz wedge dx. So here I just left out dx2, so I put the minus, etc. Whoops, except I had separated myself wrong. Okay? I'm claiming that this should be the area, the surface area,
That surface
freeform
volume, I guess.
for the sphere.
Is that surface area or volume?
It's really a volume, but it's not four-dimensional volume, it's three-dimensional volume on the surface of the sphere.
Say that again.
It's three-dimensional volume living on the three-dimensional sphere, which is in 4 space. So it's analogous to two-dimensional area on a surface living in R3, or length on a one-dimensional curve living in R2. All right?
So, sorry, just to recap. 4-dimensional equivalent of surface area.
Yeah.
So you could call it surface volume.
Right, I could call it surface volume.
Maybe you could use four-dimensional.
I mean, what math people do in higher dimensions, once you get past curves and surfaces, you just start saying blank dimensional volume. So this is three-dimensional volume. If I'm doing an integral of a 4 form in R4, that's giving me four-dimensional volume. Which is, of course, how I want to do. Oh, I didn't tell you the problem. Integrate sigma over the 3 sphere, please.
So find the surface volume.
Now, one thing I hope you've learned by this point is you would rather do a double integral than a line integral, and you would rather do a triple integral than a surface integral. Because every time you want to do a line integral or a surface integral, basically you've either got to be very lucky and have some trickery, which Haley's getting better at, or you have to parameterize and pull back. When you have to do an area integral over a region or a volume integral over a region, you don't got to do no pullback. All you do is do a triple integral and do an iterated integral. What would I rather do then, rather than trying to parameterize goodness knows how, what would I rather do to do the integral of this over the 3 sphere? Do what with the form?
Take d of it.
Take d of it. Is it a smooth form everywhere so I can actually make sense of Stoke's theorem? Sure, it's smooth everywhere. So sigma is actually a smooth 3 form on all of R4. So I can use Stoke's theorem any way I want to, but if I could only think of a 4 manifold with boundary whose boundary was the 3 sphere. I can't think of one.
Would it be the 4 sphere?
Oh gosh, what if it's just a building?
So it'd be the
Yeah, what would
ball.
you do for a 2 sphere in R3? You'd fill it in with a
Ball.
ball. What should I do with the 3 sphere in R4? Fill it in with the ball. That's going to be my 4 manifold.
Wait, 4-dimensional ball?
4-dimensional ball. So let's let M be what I'm going to call it D4, which is going to be the closed ball of radius 1, centered at the origin. Then the boundary of M is exactly my 3 sphere I'm interested in doing my integral over. Okay, so here we go. By Stoke's theorem, the integral of sigma over the sphere means I'm integrating sigma over the boundary of M. So I should just integrate d sigma over M. Pray tell me what d sigma is.
It's just 4 dx1, wedge dx2, wedge dx3, wedge dx4.
Thank you. Everybody understand how Dennis got that? So d sigma is 4 times the usual 4 form on R4. So, cool fact, which maybe you might have guessed, the 3-dimensional volume or surface area of the 3 sphere is going to be 4 times the volume of what's inside. Is that analogous to something you know?
Yeah, so that.
So we're going to say the area
4 pi r
of
squared.
S3 is 4 times the volume of this 4-dimensional ball.
Yeah, it's like analogous to
Yeah.
dimensions.
4 pi r squared.
Pi r squared.
4 pi is 3 times 4 pi over 3
Which is the surface area.
is 3 times the volume.
Yeah.
2 pi, which is the circumference of the unit circle, is 2 times pi, which is the area of the unit disk.
So we can,
So there's some recursive thing going on here as you go up.
Is that a, does that lead to all of the kinds of math, or is that just kind of a neat pattern?
It means that factorials and gamma functions are involved in volumes of spheres and balls.
Yes.
Okie dokie, so we got to do this integral, and you have web work like this. You should consider yourselves very lucky, because in past years I haven't done this example, and people have had to just figure it out for themselves on web work.
Thank you.
You're welcome.
Thank you, gracious one.
So, how do we want to integrate over the solid ball in 4 space? This is where this discussion of how you should think about it comes in. I want you to think about the 4 ball by analogy with the 3-dimensional ball in R3, where you get polar plus Z for cylindrical. Now let's do spherical plus X4 or W or whatever for cylindrical in 4 space.
How would you prove that that works, or will that just become evident?
Couldn't you simplify it and have it like as a double integral?
I don't, well, maybe, but conceptually, this is what we're doing. So Daniel, how would you prove that I can do cylindrical coordinates in R3? Well, you just do it, and then you check that you have a parameterization.
Okay.
And it's the same. Once you believe you can parameterize R3 by spherical, and then you just use your 4th coordinate, there's really, I mean, there is a problem where spherical has a problem in R3, so you have to leave out a little bit of stuff to make it officially a well-defined parameterization.
Where would that be an issue?
Well, like at the origin, for example.
Okay. But, right, since it's a, since you only have equals 1, do you need to worry about that?
No, I'm integrating over the whole ball now.
Okay.
So it's just like when you do, you guys have never once stopped and worried when you do spherical coordinates on a ball.
That naive.
You've never stopped and worried about, oh, this isn't really a parameterization of the origin. You've never worried about it with the origin and polar.
So let's not worry about either.
So I'm not going to worry about it. All right, here we go.
is this spherical in R4?
Say again?
Is this spherical in R4?
It's more like cylindrical.
This is,
No, is there?
is there, yes. So you can define n-dimensional spherical coordinates by having a row and n-1 angles.
Would that angle go used?
I'm not going there now. There was a challenge problem that no one did at the end of section 7.6.
Yeah, I remember that.
No one has done.
So if you're interested in 4-dimensional spherical coordinates, do that challenge problem. This is going to be my new out for these questions I don't want to deal with. Do the challenge problem, damn it. All right. So here's my picture. Ball in 4 space. I'm imagining iterated integrals where I do, as I trained you to do cylindrical coordinates, I project the region into my R3 here. What do I get when I do that? Not a sphere, 3-dimensional ball. So when I project it, I get the filled in ball in 3 dimensions.
Wait. So is the difference the sphere is just the shell of it
Yes.
and the ball is everything?
Yes, I've been meticulous with that language all through the course.
Yeah.
Circle is not the same as disk or ball. All right? For each point in this region, remember how we set up iterated integrals? You ask yourself,
So,
what does x4 do? Well, it enters here and exits there. By symmetry, I'm going to erase the bottom and just let it start at the x4 equals 0 and double the answer. So I'm going to say the answer is going to be twice the integral, and I'm going to set this up as an iterated integral. So maybe I'll write it this way first, just to make it clear. I'm going to take the unit ball of radius 1 and R3 for my outer three variables, and then for each fixed point here, what does x4 do? Well, it goes from 0 to, what's the equation?
1 minus x1
Not done. And then you integrate dx4 to do that, right? And then you're doing dv, integrating over the three-dimensional region. Just like when I set up cylindrical the very first time, we said z goes from blah, 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 dz, and then we put dA, and then did that in polar. So, if I switch to spherical coordinates now on D3, on the ball in R3, how do I write this? dx4 is still dx4. And what happens to dv? Spherical coordinates.
Rho sine c squared.
Rho
Rho squared sine c.
sine phi.
Dρ.
All right, give me limits.
Alright, so 0 to pi for theta. 0 to pi for
Ah, I fooled you. But I didn't have to, right? I was doing only the upper half ball here.
You're only the upper half ball on R4.
Does that also
Ah!
Yeah, but
Very good.
Does
So
that
we're
also
still doing the full ball in R3.
so
So
how
it's
is that?
still 0 to pi.
Okay.
Go on.
Okay. And then 0
0
to 1.
0
And
to
then
1,
zero to one
square root of 1
minus-
minus rho squared.
Dρ comes out.
Okay. Everybody got it? I assume you all have the answer by now.
Multiple pi.
What part? Well, most of this is easy, but there's going to be something that isn't. So, again, as usual, the theta stuff doesn't depend on anything, so we're just going to get a 2 pi. Is there anything involving phi that appears in the inner limits here? Oops, I put that wrong. Well, there's the integral of sine phi, but there's no phi involved here or here. So I'm going to get the integral of sine phi from 0 to pi, which is 2. And then I'm left with what's left. What's the integral of dx4 from blah to blah?
Square root
Oh,
of
square root of 1 minus square.
Yeah, it's just x4 from here minus here, so I'm going to get square root of 1 minus rho squared
Times rho squared.
times rho squared. And this is where you cry, because almost always when we did polar coordinates, this was an r instead of an r squared, and so we were exulting, and now we're not exulting. But this isn't that bad.
We're going to do,
How do you do an integral like that?
Isn't there like some
You
tricks?
say by parts, or
Tricks.
trig substitution. And I'm not going to take the time to do it. You guys can do this. So do this either by parts or by trig substitution, or if I know you well enough, since it's not on a test, how are you all going to do it? Of course. And this actually comes out to be pi squared over 16. And I actually did do it. So you get pi squared over 2 is the answer for Oh, but there's a 4 times the volume, so the final answer is,
You already had a 4.
no,
Oh, you didn't?
that 4 I didn't carry through. So the area of the 3-sphere is 4 times this. This is the volume of the unit ball. 4 times it is the area of the 3-sphere. Yes, please.
I know that's applied to you.
Hmm?
Because it's pi times pi squared.
Oh. I miswrote. Thank you. It was right here. This was a pi over 16. That was a typo. Yeah, okay.
Alright, so how did we get, when we had the big integral over there with 4,
Yeah.
okay, how did we get from there to the 4 pi times 2 again?
I did what we usually do is I worked my way from the outside in.
So yeah,
Because
because
integral d theta isn't going to depend on anything, so that gives me a 2 pi.
Yeah.
Integral sine phi from 0 to pi isn't going to depend on the inner stuff, so that gave me a 2.
okay, and then now it was,
But did I lose this 2?
well, no, I wonder.
No, 2 times 2 pi.
What, okay, so, and then it was dx4, is that the
Integral dx4 is
just
just
x4?
x4
And
from
then-
there to there, so I just get that.
Yeah, okay.
So did we calculate the quote-unquote surface area of this 3-sphere?
The 3-dimensional surface area is this.
Right. Okay. So not the interior ball.
That's this.
Right.
The volume of the ball inside is pi squared over 2.
So why is this different from the volume of a filled-in unit sphere in R3?
Why shouldn't it be? What does the volume of the filled-in unit sphere in R3 have to do with the length of a circle? I mean, I don't see what you're looking for here. I mean, you can, if you want to do this by Calc 1 methods, you can imagine slicing by planes this way and integrate the volumes of the cross-sectional things. And then you would integrate the volume of 3-dimensional things, dx4, and you would get something where you could do it the way you're thinking about it. But you'd have to do an integral.
And these planes would look like something 3 space?
It would look like 2 spheres.
It'd be,
No, they'd be 3-dimensional balls of shrinking radii as you move up.
Wait, how can they be 3-dimensional balls?
Because this is in 4 space. So if you slice a 4-dimensional thing, you get a 3-dimensional cross-section.
Right.
Is there a good representation?
Is there what?
As you do this more and more, do you get a better idea of what this would start to look like, or is it just abstract?
I kind of remembered a video where I saw like they put it analogous to a sphere passing through a plane, and that over time, and how that would look to a flatlander.
I mean, you really have to, I can't, there are people that do 3- and 4-dimensional topology. Those of you who have taken a course or will take a course from Wilkazes or Gordana Matic will see people who work with those things for their livelihoods. Most of my personal research has been in even higher dimensions than that, working with complex objects, and so my viewpoint is you learn to think by analogy. And so I'm trying to teach you to do it this way, by analogy. You're not literally going to picture 6-dimensional manifolds.
So will your analogies be like, oh, here's a point going to the R4, and then R4 looks like a point going into R3?
Yeah, you have to use high-dimensional representations by small
We
dimensions.
would use Calc 1 methods, we wouldn't even need Stoke's theorem.
Right, no, right.
The surface
Stokes'
area.
theorem just gave you an easy way to see that the surface area was related to some constant multiple of the volume inside. That's all I use Stokes' theorem for. And you don't need Stokes' theorem to prove that. You can do that directly. Okay, so I now want to do the first bit of discussion of something that's going to be a major theme for the next week or so, which is Gauss's law. So we're going to see more of this next week. I am on Monday going to talk about proving Stokes' theorem. I know you're all on pins and needles waiting for that.
Stokes here?
That's way too many.
Stokes' theorem and Gauss's law. So,
That's way too many
That's a lot of
S's.
in grammar books.
so
Is that 2 S's?
No.
It's 3 S's.
It's G-A-U-S-S.
You can leave off the last S.
English major.
All right, guys. Now, so, analogous to our famous one form, why was this one form famous?
Not exactly.
It was closed,
Banana.
but not exact. Now, I actually told you about a 2 form in class that was analogous to it. You've all forgotten it. But it showed up in web work,
Yeah, it was,
but you've still forgotten it.
I think Reese has it.
wait, no, spotlight.
Yes?
Okay, it was like 1 over the square root of, in parentheses out in front. Alright, 1 over the square root of x squared plus y squared plus, oh yeah, okay, not square root, times,
Wait, does it have a power on it?
I thought it was 3 halves.
3 halves is
Yeah,
correct.
yeah.
I knew there was square roots involved,
And then,
okay, x, dy wedge dz plus y, yeah, these are 6,
plus the standard area form on the sphere, basically.
yeah.
So you're scaling the area 2 form on the unit sphere by 1 over radius cubed. And you will recall I showed you that if you pulled this thing back by spherical coordinates, we did this in class, pulling back in spherical coordinates, this becomes, so notice that this is scale invariant. If you stretch the position vector by a factor of lambda, you pick up a lambda and a lambda and a lambda, so you're picking up a lambda, and what happens to the denominator? Lambda cubed. So it's invariant under stretching, just like this guy was in the plane.
So rho won't be.
So there's no rho in it, and in fact there's no d rho either, and it just becomes literally sine phi d phi wedge d theta. So it looks like the area 2 form on the unit sphere everywhere in R3. No scale factor according to rho. You've scaled out all the radius. Why does that mean this form is closed? There's no function of rho here, so when you differentiate, all you get is d phi wedge d phi wedge d theta. Alright? So it's a closed 2 form. Is it exact?
No.
Humpty Dumpty asks.
No.
Why no?
Because it's analogous to the first one.
That's what work said so.
Because you put it up there.
You can do better now. You've got,
The origin. The origin's.
yeah, the origin's an issue, but so what?
You can take D at the top one.
Not it. By the way, I should say this is a 2 form on R3 minus the origin. The origin is not on the domain
Okay.
because this is not defined at the origin.
I guess because analogously the supposed v where dv equals omega would be on 1 form on R3 minus
Yeah.
some plane.
Well, but hang on. Let's think about analogous proofs that we did to nail the fact that this couldn't be an exact 1 form. We did something with the fundamental theorem of calculus to see that. What should I now be using? Stoke's theorem. Could omega be exact? What did we say was true as a consequence of Stoke's theorem? Take the sphere, I don't care what radius, what do you get if you take any sphere centered at the origin? Say the unit sphere. What is the integral of omega over S? You're integrating this 2 form. What is that? What did we say that was?
Surface area?
The surface area is the area 2 form of the sphere. That's what this is, right? On the unit sphere, this is the area 2 form. This is all 1. Is the area of the unit sphere 0?
No, it's something.
What's the area of the unit sphere in R3, the usual sphere? What's the integral of this over the sphere? It's 4 pi, surface area of the sphere. So we've gone from 2 pi integrating this guy to 4 pi integrating this. How does this show this can't be, that omega can't be exact? Well, you have to soup up by dimension.
Yeah, I can see it. Yeah, doesn't Stoke say something about being different? About 4 pi.
What? The two-sphere is a compact two-manifold with boundary. What's the boundary of it? Nothing.
So it's not, what?
If omega were d of somebody, the somebody being a one form, we would have the integral over the sphere is the integral of d eta over the sphere, and by Stokes, I don't have green chalk for Stokes anymore. This would be the integral of eta over what?
Boundary of this.
The boundary, which is nothing. So this is 0. Remember we gave an alternative proof of this for those of you who didn't like that by cutting this manifold up into 2 pieces. Well, is the integral 0? Therefore,
Doesn't work.
omega can't be exact. All right. And so completely by analogy with what I did for you with curves, let me ask you the following question. Suppose I take some bizarre compact surface, compact oriented surface in R3. No boundary. What is the integral of this omega over m? Always?
If it's exact.
It's not exact.
I don't know, it's hard to say.
No. Remember the game we played with that guy? It depends on whether the origin is inside the surface or not. It's a two-dimensional version of the winding number stuff. The answer is going to be it's 0 if the origin is not inside of m. Let me just write that in words. Is not inside the surface. But what happens if it is inside the surface?
It's too high.
Then you put yourself a tiny little sphere around the origin, and what's the integral of omega over the sphere? 4 pi. Apply Stokes' theorem to the region between the little sphere and the big surface. We'll do lots of this next week. You get Stokes' theorem does apply, and you find that the integral is 4 pi.
So for however many closed loops there are in, I guess, is it R4, 3?
Well,
Then
so
there's
it's hard to make surfaces loop the way you make curves loop, but it's analogous to that.
Okay.
If you took some surface that crossed through itself and wound around the origin more than once, you would pick up that many 4 pi's.
Okay.
Okay, we're done for this week.
By inside.